In the last video, I was able to get a window to appear on screen using nothing but standard C and Win32, Windows' native library used for development. So in order to get things rendering onto that window, I skimmed through Win32's documentation to see if it offers anything for graphics rendering, and there's a few confusing options, but the one that has the most important features for me seem to be the GDI, or Graphics Device Interface. Now, from what I'm aware, the GDI is quite old and primitive and low level, but it does come with a few ways to render a few basic pre-built things, such as, lines, curves, images, and even text. But I didn't care about any of that because it's too high level for me. I want to have to work to render these things. I want to have more control over how all of this is decided and internally rendered. What this means more literally is that I want to be able to speak closer to the graphics processing unit, or GPU, that exists inside my computer. So I want to know how close Win32 or the GDI can get me to speaking to it directly. Now, thankfully, there already exists something that allows you to talk pretty close to the GPU without actually having to worry about what brand GPU it is or what model, and these things are known as graphics APIs, and you might have heard of them before. When you boil it down, graphics APIs are pretty much just big standards that list a bunch of functions and such that are all meant to collectively build up and allow you to do things. Different GPUs then provide implementations for these standards, allowing you to talk to any GPU that supports the standard without having to worry about what specific GPU you're talking to. For example, and this is going to be a major oversimplification as you will come to figure out through the runtime of this video, if the function drawSquare existed in a graphics API, every GPU that supported the graphics API would have an implementation of the function drawSquare that all do approximately the same thing. If you ever wanted to just draw a square, then you could just use the graphics API and call the function drawSquare, and it'll work pretty much the same on any GPU that supports that graphics API. You now have a way to say one thing and have it work on a bunch of other things, because all those other things agree on what that one thing is and what it means and what it does. Does that make sense? And that is the essence of a graphics API, just a collection of agreed upon functionality that a lot of GPUs support so that you can use all of the GPUs pretty easily. There are three big players in the ring, so to speak, when it comes to graphics APIs as of the making of this video, and that is OpenGL, Vulkan, and DirectX. All of these APIs are meant to provide fairly low-level and fast rendering methods using the GPU, allowing for tight optimizations and customizable rendering techniques, and overall just allowing your video games to look all realistic and shiny. OpenGL and Vulkan have the most in common, and you'll often hear both of them in discussion at the same time. They're both a cross-platform graphics API developed by the same company, Kronos. Now, OpenGL is way, way older than Vulkan, which means that support for it on GPUs is amazing, but it's not going to be the fastest, most up-to-date graphics API to use. Vulkan is the opposite of this. It's really new, which means that it has a bunch of cool features and you can get really optimized with the way you render things, but unfortunately, it's not going to have the same level of support as something like OpenGL. In other words, OpenGL is old and slow but works with everything, and Vulkan is new and fast but may not work with everything. The big advantage of both of these is that they're both cross-platform, which means that the code that you write in the graphics API will work pretty much the same on any device. Now, DirectX is the ugly exception to this. It was developed by Microsoft purely for Microsoft machines, meaning that its compatibility is about as bad as you could theoretically get. So in terms of which graphics API I want to use, I have to throw DirectX off the table. I've been stuck in the weeds of Win32 for quite a while now, as you may know, and not only am I completely disillusioned with it, I just want the meat of my graphics code to be cross-platform. At least for now, I don't want to have to go back and rewrite all my graphics code when I'm going in to support another system. I just want to be able to keep that issue entirely quarantined in muCOSA for now, so I'm gonna want to pick a cross-platform API. So this pretty much just leaves OpenGL and Vulkan on the table, and I'm inclined to pick OpenGL for several reasons. The biggest reason is that OpenGL is dramatically easier to use than Vulkan, and I want things to be easier for me this first time around. And OpenGL's very good compatibility is also a nice bonus. Now, even though OpenGL itself is cross-platform, loading OpenGL needs to be handled by the operating system, meaning that I need to go back into muCOSA to implement OpenGL loading. I tricked you! You thought we were done with muCOSA. Nope, we're still, I promise we'll be done with it soon. Okay, I promise. So the way I implemented OpenGL in muCOSA goes as such. Ahem. An OpenGL context can be created using a window, and once it's created, it is eternally linked to that window. The OpenGL context exists until rather the context itself or the window is destroyed. The creation and destruction function look like what you'd expect them to look like, with the creation function taking in what OpenGL version you'd like to load, since there are multiple versions of OpenGL. Once an OpenGL context has been created, you can use it by binding it. Once an OpenGL context is binded, all subsequent calls to an OpenGL function will be performed relative to that OpenGL context in its window. To find an OpenGL function, and yes, you need to find OpenGL functions before you can call them, I created the getProcAddress function, which can be used to locate an OpenGL function by name. And finally, in order to present what you've rendered onto the window, I created this swapBuffers function. What swapBuffers means exactly isn't relevant to the scope of this discussion. You can just think of it as meaning render the stuff onto the window. And finally, as an extra cherry of customizability on top, I added an extra feature to the muWindowInfoStruct, which, if you'll remember, can be used to customize things about the window upon creation. The extra piece of information I added was the pixelInfoStruct, which allows you to specify a lot of things about how the pixels of the window are actually internally defined and stored. You can customize stuff like the amount of bits per color channel and a bunch of other complicated stuff that I'm going to get to down the road in this video, like the stencil and the depth and the samples. So, like usual with all this defined, I now need to go ahead and implement it in Win32. So here's a cool thing. Virtually every window in Win32 is associated with a device context, which is used to interface with the GDI. Now, if you watched the previous video and you have insanely good memory, you'll remember that upon each window being created, I take its device context and internally store it for later. Well, now is that later, and I can now use the device context to do anything that I would be able to do with the GDI. In particular, the ability to create an OpenGL context using the function wglCreateContext. So great, just create a window, get its device context, and then use that to create an OpenGL context. This all seems fine and good, right? Well, nothing is easy in the land of Win32, and you may notice that the wglCreateContext function doesn't actually allow me to specify what version of OpenGL it actually creates. If I want to specify the version, I have to use another function called wglCreateContextAttribsArb, but this function is an extension and needs to be actually manually loaded. And wouldn't you believe it, in order to load extensions, I need to already have an OpenGL context created. In other words, I need to create an OpenGL context to load an extension to create an OpenGL context with a specified version. So this is a supremely stupid situation to be stuck in. How exactly do the fancy websites tell me that I should get out of this one? Well, the common solution online seems to be to create a temporary OpenGL context whose sole job is to just load that better loading function. Once you have the better loading function, you can just destroy that OpenGL context and hold on to the loading function for later when you need it. So that's what I did. If the user requests support for OpenGL, the first thing a muCOSA context does upon being birthed into existence is create a temporary OpenGL context to figure all this out. It uses this temporary context to find the better loading function, as well as any other functions that may need to be loaded in advance before creating an OpenGL context. Once everything is found, the temporary OpenGL context is destroyed, and the location of all these functions is stored for later. When later comes, and the user wants to create an OpenGL context using a window, the better loading function has already been loaded, and so now I can just use the better loading function. So now I can use the function to create an OpenGL context that uses a specific version using this weird integer formatting that I can't be bothered to explain. It took me this huge mess of switch statements to take a muCOSA OpenGL version value and convert that into the integer formatting that the function will actually understand. And isn't it just beautiful? I love it. Okay, but besides that shababble, there's very little that needs to be done for the OpenGL context besides specifying the pixel format, which actually needs to be done before the context is created. The GPU already has a defined set of pixel formats that it supports, so I need to take the user's pixel format that they specified and find the closest match that the current GPU supports. The function that exists for this in Win32 is choosepixelFormat, and it uses some more weird integer formatting for specifying specifying what the pixel format's actually made up of. However, I had a very hard time figuring out how this integer format actually works, and what you see here is essentially a bunch of internet examples I could find stapled together, and it works on my device, so yeah. Just know that it takes in the muCOSA pixel format and translates it into some integers that OpenGL can understand, apparently. This all comes together to create a beautiful, version-specific, pixel format-specified OpenGL context, all wrapped up into a nice, beautiful HGLRC handle. Isn't it just amazing? You know, I'm so glad that loading OpenGL in Win32 is so easy and intuitive. You need to use the outdated and legacy GDI among all the other graphics options, duh, which is then used to load an OpenGL context to then load an OpenGL loading function, obviously, which is then later used to actually create OpenGL contexts. This process is confusing and really poorly documented. Virtually all the information you see here I got from just scouring random, very old forums and websites, especially the values for all those OpenGL pixel format attributes I was talking about before. I'm still convinced that I'm doing something wrong secretly that I'm unaware of, but it's Win32. What are you gonna do? How is this API the backbone of all Windows software? Actually, no, that would explain a lot of things. Thankfully, virtually all the other stuff for OpenGL is super duper easy to achieve. You know, WGL delete context for deleting the context, WGL make current for binding the context, swap buffers for swapping the buffers, wow, really? And WGL get proc address for locating an OpenGL function. Ignore all of the C99 sorcery you see on screen right now. Or pause and read this explanation if you're a super duper nerd. In order to test if this all works, I wanted to create a little demo that does some basic OpenGL rendering, but I also wanted it to be a little bit fancy since, you know, I've come this far and I want to enjoy the fruits of my labor. So I created this demo. I'm not going to get into the details as to how this works because, trust me, I'll get to OpenGL in a moment. But with some matrix math blatantly stolen from CGLM, some basic shaders, vertex data, and some mild debugging, I got this cool rendering cube. I have a secret to tell you. I still need to work on muCOSA because there's a few things I need to add before we're done with it. I tricked you again. We're still working on muCOSA. This is largely just miscellaneous stuff that I kind of need to get out of the way that I might use in the future before we can continue on. So I'll try and be brief with this. I promise. The first thing I created was a key state key map. Much like the keyboard key map, which exists as just a list of values indicating whether or not certain keys are up or down, the key state key map is a list of values indicating whether certain states are on or off, like numlock, caps lock, and scroll lock. In Win32, the function getKeyState exists, which allows me to retrieve whether or not a certain key state is on or off, so every frame I just use this function to update all of the key state values. I don't like having to check every key state every single frame to update these values, but I couldn't find a way in Win32 to do it whenever the user changes a key state, so I kind of just have to do it like this, I think. The next miscellaneous thing I implemented were minimum and maximum dimensions, which can be used to specify how tall or wide a window can be at minimum or maximum in pixels. For this, I added optional minimum and maximum width and height values in the window info struct, allowing the user to specify these values upon a window being created. Now, let me ask you a question. How do you think Win32 would allow you to specify these values when creating a window? Probably in the window creation function itself, right? Well, no, it isn't there. Well, is there a separate function that allows you to set these values for a given window? No, that doesn't exist either. What you should have predicted was an event that you have control over, where Win32 sends you a message to request you for these values whenever it needs them, using the lparam value as a pointer to a struct that you dereference and fill the values into. Perfectly predictable and reasonable. Okay, ignoring that. Next random thing, the scroll level. On a lot of software, you can use the touchpad or the mouse scroll wheel or whatever to scroll up and down. As far as I'm aware, this is usually implemented with a scroll level, which is basically just an integer value that smoothly increases and decreases automatically as the user scrolls up and down. So I just made the scroll level a window attribute that you can retrieve at any moment. Internally, this is achieved by storing a scroll level value in each window, and this is initialized to 0 upon the window being created and is updated by responding to the event WM mouse wheel. To test this feature, I made a demo where the window moves up or down in accordance with the user scrolling. Every frame, I retrieve the scroll level, and if it's different from the last frame, I calculate the difference and then move the window's Y coordinate based on that difference. Okay, next thing, callbacks. I briefly mentioned these in the previous video, but a lot of libraries similar to muCOSA allowed the user to set up their own functions to be called whenever the user does something, such as when a user presses or releases a keyboard key. These functions are commonly referred to as callbacks, and they allow the user to set up a piece of code that gets automatically called when something happens, instead of, checking each frame to see if it happened or not. For defining these in muCOSA, I made the struct muWindowCallbacks, which acts as just like a container for every single callback function that can be optionally set by the user. This container contains callbacks for various things, primarily, callbacks that are mouse and keyboard input related, or for when things about the window get changed, such as it moving. I then included this struct in the muWindowInfo struct, allowing the user to specify any callbacks for a window when creating it at first. I then also defined a bunch of separate window attributes that can be used to set certain callbacks after the window has been created. And, admittedly, unlike most things, this was pretty easy to implement in Win32 because Win32 already sends you messages when almost anything happens to a window, meaning that I can just intercept these messages and then call the corresponding callback function when needed. Some of these message types for these callbacks were types that I hadn't implemented yet, such as WM size for when the window's size changes, so I quickly added them, with their only job being to call any callback function that might have been set by the user. Some of the other message types, though, I was already intercepting, such as the WM key down and WM key up messages, which were already being used to update the keyboard key maps, so I just stapled the callback code to the end of those functions. There was some classic Win32 sorcery involved when trying to get some of the relevant values for some certain message types, such as trying to get the window's position from the message WM move, but once again, and as always, Google.com proved my savior. Okay, I'm going to spare you a lot, and trust me, a lot of gruesome detail when talking about this next feature, but oh my god, text input was so much pain. I'm sure there's some better way to do whatever I'm doing here, but I couldn't find any other better way, so this is what I did. Text input in Win32 is usually handled with little, graphical interface boxes, which, as far as I'm aware, automatically handle a lot of the meat of the logic regarding letting the user type into the boxes and then retrieving what the user actually typed. However, I don't want to use Win32's graphical boxes because I'm planning to handle my own rendering using OpenGL, so I need some way, some no-nonsense, no-strings-attached way to receive text input without actually changing anything visually, just raw receiving text input. I could just manually keep track of every single key being pressed and then figure out all the text input myself, but not only would that be excruciatingly difficult, it would probably only work with English keyboards and English text. Win32 already has its own fancy system for allowing the user to type non-English text using any keyboard, so whatever system that I come up with here probably should be compatible with that. Thankfully, Win32 already has something for this. It is the IMM, or Input Method Manager, and it is, to this day, probably the most poorly documented thing I've ever had to work with. Win32's app development page, where I usually get this sort of information from, listed a bunch of features that I was never going to use, or use cases that I wasn't particularly concerned about. Apparently, somebody was holding a gun to Microsoft's head, telling them to write this page without ever just saying how to use most of its vital functionality. But with enough scouring of random code repositories and scraping together all the samples I could find, I was able to build a system that should work from what I could tell. But for some reason, it literally just wouldn't work. Like, sometimes it would receive input, but it would just be jarbled or nonsense, and sometimes it just wouldn't send any input at all. I could not get it to work, and I had no clue why. And after spending literal days, or at least what felt like it, of just going through each line of code and brute force checking and playing around and seeing what does and doesn't work, I was eventually able to get it to work, and all I had to do was go to this random line of code and not specify which window I'm processing events for, and use the non-UTF-16 version of this function. I don't really understand what that did or what that has to do with anything, but this is the only way that I could get it to work. I think the documentation says something about it, but I'm literally just too tired to care at this point, and I was just glad that text input was working, and I even set up a little nice demo to set the window title to whatever character the user typed, so ultimately it was worth it in my opinion. And finally, the last thing I implemented, and then I promise I'll get to graphics, is getting and setting the clipboard. You might think of the clipboard as being used purely for text, simply copying and pasting whatever text you'd like from one application to the other, but clipboards can actually be used to pass different types of data, such as image data. You can copy and paste image data from some applications to others. But for now, just for the sake of simplicity, I pretended that you can only copy and paste clipboard text. That's the only data type that clipboards could theoretically hold, and I'll probably come back later and implement other clipboard data types. In muCOSA, I just created a simple clipboard get and clipboard set function. And then implementing these in Win32 entails converting between muCOSA's UTF-8 and Win32's UTF-16 character encoding. And you also have to mess around with some global memory because the clipboard is global memory. It exists across the entire system for all applications, but I won't get too in the weeds for that. And that's pretty much it for the non-graphic stuff. Time to get things rendering. As a display of my true creative brilliance, I decided to name the library that will handle graphics muGraphics, which I will shorten to mug, which I think is really funny. Much like muCOSA, and this is more elaborated upon in the previous video, mug is encapsulated within the idea of a context, which is created by the user in order to use mug and then destroyed to free all of the resources being used. Virtually each function in mug is executed relative to a context, allowing each context to be fully encapsulated with no global dependencies. The mug context is the context in which mug does its stuff. Now, before going any further with mug, I wanted to establish one solid rule that I wanted to follow for the rest of this development, and that is that rendering code is separate from anything else. What this practically means is that all of the code that's tied to whatever system we're running on, such as creating the window and creating the OpenGL context and all that other stuff, it exists entirely in a different space from the actual raw OpenGL code that I'm going to be writing. I care about this because I don't want to have to rewrite any of my rendering code based on whatever the code may actually be rendering to, whether it be a Win32 window or a Linux window or a phone app, wink, 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 wink. For this reason, at the API level, rendering in mug is done in reference to a graphic, which is an abstract representation of some surface that can be rendered to, and all of the rendering functions work with a given graphic. This means that whether or not the graphic was created from a window or from a phone app or a goddamn Nokia telephone for all I care, the rendering functions themselves do not change. All this is designed to do is effectively separate whatever surface we may be rendering on from the actual meaty rendering code itself. Additionally, each graphic draws to the screen using a graphic system, which represents which graphics API is being used by it. Currently, this can only be OpenGL, but I've set this up so that in the future I can come back and implement other graphics APIs, such as Vulkan. This all compounds into a system where once the graphics API is decided and what object it's going to render to has also been decided, a graphic can be made. And from then on, the rendering code is all the same, no matter what graphics API or object the graphic came from. Rendering code is separate from anything else. But like all things, this is much easier said than done, since all this rendering code being separate from everything else needs to be worked out internally. But it was actually easier than I was expecting it to, and this is because OpenGL is already a cross-platform graphics API, meaning that its code is already pretty disconnected from whatever we may be rendering to. In fact, once an OpenGL context is binded, virtually all OpenGL functions work pretty much exactly the same regardless of whatever it's running on. All I ended up having to do internally was create a struct which holds some handle to whatever was used to create the graphic, as well as a value that indicates what that handle points to. In this struct, I also store a value that indicates what graphics API that the graphic is using, because I'm probably going to support other graphics APIs in the future. The struct that holds all of this, which I creatively named muGraphic, is then internally used to refer to a graphic and interact with it. Using this, I'm able to define a function that cleanly and quickly creates a graphic using a muCOSA window, filling in all of the values as it needs to. And then from there, I created a handful of internal functions for the graphic, which are designed to be usable no matter what was used to create the graphic initially. Take, for example, the function muGraphicDim, which retrieves the dimensions of a given graphic. This task is heavily reliant on what was used to create the graphic, so all this function does is do whatever needs to be done based on what was used to create it. In the case of a muCOSA window, which is the only case for now, this simply calls the muCOSA window get function and does all the stuff needed for that. This system is needed because, for example, if I ever came back and implemented support for creating a graphic from a Nokia phone, I would add that case to this function, along with the code for retrieving the dimensions of the Nokia phone. This function wraps all that complication inside of itself and allows me to just use this function without ever worrying what the graphic was created from. Internally, I just create and use a set of these functions for interacting with the graphic, including functions for destroying the graphic, checking if it still exists, updating it, etc. Now, even though I said that OpenGL is cross-platform and its functions are very disconnected from whatever we may be rendering to, several small yet vital parts of OpenGL still require you to interface with whatever is being rendered to, such as creating and binding an OpenGL context. So I created a few graphic functions specific to OpenGL, covering all of those edge cases and ultimately allowing you to use a graphic in OpenGL regardless of what was used to create the graphic. And with that wrapped up, I've now internally created another API for interacting with a graphic regardless of how it was created. I have a set of functions that I can use that will work to interact with a graphic no matter where it comes from and no matter what it was made from. And with this set up, I can now write OpenGL code that interacts with a graphic with the OpenGL code itself not needing to change based on what was used to create the graphic. This makes the rendering code fully separate from anything else. Beautiful. Okay, now I just need to actually start writing OpenGL code. And to just test if everything I've modeled works so far, I set a very simple and hopefully very easy goal. Clear the screen with this beautiful color, a slightly greenish, very dark gray, which, in case you haven't noticed, I've been using as the background color for this series so far. So the real challenge here is actually loading OpenGL. Even though I can create an OpenGL context with whatever version I like, Win32 doesn't actually provide me with the definitions and locations of all of the OpenGL functions for a particular version. I need to define and locate all of those myself. The OpenGL version I chose to use for Mug was OpenGL 3.3 Core, since it's fairly old and compatible on many machines, but still has enough features for me to chew on, and I definitely did not pick it just because Learn OpenGL chooses it. And oh boy, is OpenGL 3.3 Core actually quite large. So, unfortunately, I am going to break a sacred rule of this project so far and import code written by other people. GLAD. Well, in reality, GLAD is a tool that generates code that defines and locates all OpenGL stuff for a particular version. So I'm using GLAD to generate code for 3.3 Core and copying and pasting that into my code. It's unfortunate, yes, but either way, the code is generated based on OpenGL specifications. So even if I were to write it myself, I'd still just sort of be copying code from somewhere else ultimately. So I chose to do it this way. It's kind of unfortunate, but it is what it is.
What are you gonna do?
Funnily enough, doing this does actually mess with my licensing, which I've neglected to bring up until now. All the code I've written so far is under a dual license for both the MIT license and public domain. I'm not a lawyer, but the STIB libraries use this license, and apparently it's very forgiving and allows you to do virtually anything with the code, so I've just put all of my libraries under this license. Using GLAD itself doesn't conflict with my license because the generated source code that it's given me is under a public domain license. But guess what? OpenGL specifications, aka the actual raw definitions of OpenGL as a graphics API, are under the Apache 2.0 license, which does conflict with my license since it isn't public domain. And since this license is attached to OpenGL's pure and raw specification, like the actual literal definition of OpenGL and its particular versions, if I use any OpenGL loader, even if I wrote my own, I have to comply with OpenGL's Apache license. Now, realistically, I don't have to worry too much about this, and this is where I have to set a huge disclaimer that I probably should have set before starting this entire rant. None of this so far has been legal advice, and I'm not framing anyone, including myself, as giving anyone permission to do anything illegal. That being said, many projects that load OpenGL ignore the Apache license, with Khronos not doing anything, and some very informal advice from some very non-representative people working at Khronos have said not to worry about it. Ultimately, all this changes about my project is that I license all of my source code, meaning just the actual code itself, like as a file, under my normal license, and then I just attach the Apache license to the end of my license, stating that it's for Khronos' specifications. It's an unfortunate situation to be in, yeah, but it doesn't upset me all that much since it doesn't really change my project all that much, but come on, it's just such a minor dent on an otherwise very forgiving license. Okay, that's a whole mess, but after I generated all the stuff for OpenGL 3.3 core using GLAD, I just copied and pasted it into mug. This code alone is already about 3,500 lines long, but again, it kind of has to be done to use OpenGL.
What are you gonna do?
With that out of the way, I can just use this basic setup to get GLAD to load all the OpenGL functions for me, and just like that, I now have OpenGL at my disposal. OpenGL is fairly minimal, so you don't really need to know or interact with many functions to do what you need to do. Thank God! So thankfully, there's only a handful of functions I need to care about right now just to clear the screen with a color. The first function is GL viewport, which updates OpenGL's screen resolution with whatever it should be. For this function, I just keep it updated each frame with whatever the resolution of the graphic currently is. Doing this keeps OpenGL's screen resolution updated with what the dimensions of the graphic are at all times, which is currently just the dimensions of the window. You can resize the window, and OpenGL will be informed about it and adjust itself properly. The only other OpenGL functions I need to care about for now are GL clear color and GL clear. GL clear color sets the color used to clear the screen, specified with a red, green, blue, and alpha channel. I think the alpha channel here is meant for supporting a see-through window, but I've never seen this before and I'm not particularly concerned about supporting it right now, so currently only the red, green, and blue channels are set, which gives me full RGB color range. And then GL clear simply clears a particular screen buffer, which in my case I want to clear the color buffer, so I tell OpenGL that with this value. So these two functions in sequence set the clear color to whatever I need, and then clear the screen with that color. And believe it or not, that's all I need to code in OpenGL for now, with all this wrapped up into a few nice and clean functions. The only job I have from here is setting up the higher level mug functions I defined previously to call these lower level OpenGL functions when needed. All I'm really doing here is just linking up the functions to call them when needed. It's just a bunch of boilerplate, really. I will note that the function I made to update the graphic also takes in a target FPS parameter. This allows the user to pass in the amount of frames per second they'd like to process so that the program runs at a fairly consistent rate, which makes timing a lot easier to deal with. The exact reasoning for why you'd want this and how it works is largely explained in the previous video, so just watch that if you'd like further clarification. And if you don't want Mug to try any timing stuff, you can just set the target FPS to 0 and it won't do anything. With all of this figured out, I whipped up a little demo that just creates a window graphic and runs a frame-by-frame loop. Each frame, I clear the screen with my beautiful color, swap the buffers to present it, and then update the graphic at a rate of 100 frames per second. If the user presses escape or the graphic is ever closed, the frame loop is exited, and everything gets destroyed. And after some minor bug fixing as always, I got a beautiful window with a custom color plastered on it. I have successfully cleared the screen with a color in just shy of 10,000 lines of code, muCOSA and GLAD included. Truly nothing is taken for granted here. Now that I've taken approximately 25 minutes to clear the screen with a color, really closer to an hour and a half if you include all the progress in the previous video, I will now take a considerable amount of time to set the color of a single pixel. Yes, a single pixel on my display. In reality, I'm going to be referring to it as a point, since that's the terminology most graphics APIs use for this sort of stuff. I've decided to start with point rendering because it's inarguably the easiest object to describe, and I want to start off easy and simple before we get to the more advanced shapes, and trust me, we'll get there. Understanding point rendering first will gradually ease me into how things are ultimately gonna get rendered, and there's two major steps to this: describing how it'll work in muG's API, and then actually getting it all working internally. In muG's API, I've defined a point via two things: a position and a color, as well as all of the rules that I've come up with regarding how these values are interpreted. The position is made up of 3 decimal values, which correspond to its x, y, and z coordinates. 0, 0 is the top left of the graphic, and the bottom right would be the graphic's dimensions. This means that increasing the x-coordinate of an object moves it to the right, and decreasing the x-coordinate moves it left, as you may predict. However, increasing the y-coordinate actually moves it down, and decreasing the y-coordinate actually moves it up. This may seem weird, but it's actually quite standard. In my experience, most high-level renderers I've worked with do it this way. I think it's due to the fact that rendering used to be primarily done with terminals, where text starts at the top left, but don't quote me on that. The z-coordinate is a bit special, as it doesn't actually move the object visually on its own. Instead, the z-coordinate sort of acts as a depth layer. Objects with higher z-coordinates will render over objects with lower z-coordinates, regardless of what order you rendered the objects in. This allows you to use the z-coordinate to order the rendering of objects without having to worry about the actual order of the render calls you're making, which is super convenient and definitely doesn't have any asterisks attached to it. The color is made up of 4 decimal values, which correspond to its red, green, blue, and alpha channels. In case you didn't know, different amounts of red, green, and blue are used in virtually all modern displays to simulate a lot of colors within human vision, so you can define virtually any color you'd want using just these first 3 channels. The alpha channel requires a bit of explanation though, as it corresponds to its transparency, with 0 meaning totally invisible and 1 meaning totally visible.
But muKid, I thought you said you weren't gonna support transparent windows.
Wrong! Since the screen needs to be cleared each frame with a fully visible color, that gives me a fully opaque background at any given moment. From there, any slightly transparent objects can be rendered by just mixing the color of the object with the background, using some math that OpenGL can pretty much automatically handle. You can also use this mixing to render a semi-transparent object over another object too. And just like that, you can get transparent objects rendering with absolutely no asterisks. You know, besides the asterisk that comes with transparent rendering, that's the same asterisk next to z-coordinates I was talking about earlier. The asterisk is this: rendering order does actually matter with transparent objects. Don't get me wrong, if you never render any see-through objects, rendering order is totally irrelevant, and the z-coordinates of the objects fully handle the rendering order of everything. However, with see-through objects, things get a bit messy. Take this example with these 2 squares. The z-coordinate of the slightly transparent square is above the z-coordinate of the opaque square, causing the slightly transparent square to render above the opaque square. These 2 squares are rendered with 2 different calls, and currently the transparent square is rendered after the opaque square. However, if I simply swap the order of these 2 function calls, the effect breaks. The transparent square is still rendering over the opaque square, but now it doesn't seem to be blending with it. The exact reasons why this happens are a little bit complicated, but just know that technically speaking, rendering order does still matter, but I don't think it's that big of a deal, and at most it will cause minor headaches for me in the future. Okay, so this is the definition of a point: its position and its color. However, just because I've defined a point doesn't mean that I've defined how to render one. You may think the best approach would be to just create a render point function that takes a point and renders it. Or if you really want to get fancy, a function that takes in multiple points and renders all of them. But this is hardly the most efficient approach, and most modern graphics APIs don't let you, or at least don't really want you to do this. Instead, graphics APIs primarily want you to render objects using buffers, and to explain why they're so efficient, I'm gonna need to get a bit technical for a moment. Most of the reasons working with a graphics API can get so technical stem from the fact that the central processing unit, or CPU, is very different from the graphics processing unit, or GPU. Most of the stuff my program does, such as defining what a point is and creating a list of them to be rendered, is done on the CPU, with all of the data for it being stored on its own memory. However, all of this data notably isn't being processed by the GPU, nor is it easily available to the GPU since it has its own dedicated memory. This means that every time I want to render a bunch of objects defined on the CPU, I have to bring all of it over to the GPU's memory, and then the GPU can work on rendering it. So creating a function that simply renders a list of points would entail moving over all of the object data from the CPU to the GPU each time I wanted to call the function, which is just really inefficient since sometimes the data is really similar between function calls. Instead, it'd be much better to store all of these points on the GPU and keep them there. Whenever they need to be rendered, they're already on the GPU, making rendering much quicker. It's not perfect, since if I ever want to change that data, I still need to transfer the new data from the CPU to the GPU and copy that over, but it's ultimately more efficient. By the way, don't let the term buffer confuse you. Buffer just means a collection of data that's being used to transfer data from one place in memory to another. In the example I provided, the object data on the GPU is the buffer, storing a copy of the memory from the CPU to be quickly accessed and rendered by the GPU. The idea of keeping data stored in a buffer on the GPU and replacing the data every now and then with data transferred from the CPU is implemented in most modern capable graphics APIs, including OpenGL, and it's primarily used as an efficient way of rendering data in a quick and versatile manner. So naturally, I want to use this when rendering in mug. I could implement a complex system that makes all its own buffers internally, allowing the user to just define objects all willy-nilly while I handle the buffer logic for all of them under the hood, but I think I'd have a really hard time doing this, and it would probably run slower than just giving the user control over the buffers in the first place. So Mug embraces the buffer, and it does so in the form of object buffers. An object buffer is a buffer that stores data for a particular type of object, such as the data for a list of points, which is what I'm currently working towards rendering. A single buffer can store a theoretically unlimited number of objects, given that all of the objects are the same type of object, such as having an unlimited buffer that's filled with an unlimited amount of points. Creating a buffer entails allocating a spot on the GPU's memory and then filling it up with data via copying it from the CPU to the GPU and then mapping it onto that spot. The data in question here is just a list of all of the objects that you want to render within the buffer. This data can be provided when creating the buffer, or it can be manually set later via filling the buffer, which goes in and copies that data to the GPU. You can fill the entire buffer in one go, or you can fill select portions of the buffer, which is done with the sub-filling functions. These can be used to update the data for only certain objects within the buffer. Once the buffer has the object data you'd like for it to have, you can then render the buffer, which goes in and renders all of the objects stored within the buffer. Similarly to how you can fill select portions of the buffer, you can also render portions of the buffer, which is done with the sub-rendering functions. These can be used to render only certain objects within the buffer. The whole buffer is then deallocated from the GPU once you call the destruction function on it. I'm pretty sure most modern graphics APIs automatically deallocate all resources on the GPU, since I'd imagine things could get pretty bad if they didn't, but it's good practice anyway to destroy all of your buffers manually. So, with the data for a point defined, as well as a buffer system to transfer the point data from the CPU to the GPU and subsequently render it, you can theoretically render a point onto the screen. Now I just need to actually implement all of this in OpenGL under the hood, which is easier said than done and requires a bit more thorough knowledge of how OpenGL works than the 3 functions we understand thus far. Graphics APIs are built to give you a lot of control over how things are drawn onto the screen. The most powerful tool graphics APIs give you in this regard is the shader. Shaders in most graphics APIs work as a way to directly command the GPU on how each step of the rendering process should go, giving you the power to write code that the GPU will execute. In other words, shaders give you the power to write and execute GPU code. Don't get me wrong, they're not the only way, as any good Bitcoin miner knows. Actually, I think they use ASICs nowadays or something. I don't know. But to be clear, shaders are overwhelmingly powerful. Being given direct access to execute code on the GPU to render things onto the screen is insane and can be used to render some truly insane stuff. Since shaders act as GPU code in a sense, they actually need to be written in a different language that's provided by the graphics API and eventually executed by the GPU. In the case of OpenGL, its shading language is GLSL, short for OpenGL Shading Language. Haha, very clever. And to render any cool objects in OpenGL, you need to provide two types of shaders, a vertex shader and a fragment shader, which are then combined into a shader program which can then be used to render any buffer data you want. I'm going to need a vertex and fragment shader to use for every object type that I'd need to render, so I'm going to need to start off by creating a vertex and fragment shader for rendering points. The vertex shader controls the translation of all my object data into actual vertexes that OpenGL can process. In case you don't know, a vertex, in the case of graphics APIs, so that all the geometry nerds don't yell at me, is basically a single point on the screen. In the scope of this video, you can think of the word vertex as being a fancy way to say a position. So the vertex shader specifies how to take my raw buffer data and actually translate it into individual vertexes identified by their positions, which can then be processed for rendering by OpenGL. The first thing I have to do in GLSL is define how the data in the buffer should be read vertex by vertex. In the case of the point that I'm trying to render, that's just 3 values for the points x, y, and z coordinates, and the 4 values for the points red, green, blue, and alpha channels. As a quick side note, I'd like to mention that the data in the GPU buffer doesn't necessarily have to align with the CPU data used to define each point. The data for each point is stored on the CPU, and it's the actual mug point array that the user defines. This data can theoretically be different than how I end up deciding to store it on the GPU. The vertex shader reads the data from the GPU buffer, not the actual CPU mug point array, which means that if I decide to store the data differently on the GPU, the vertex shader will reflect that. This will become important later, and will be expanded upon further, so don't you worry, but also don't you forget. Now, the job of the vertex shader is to take this data and convert it into just a position value, which will essentially be the vertex output of the shader. But this introduces a complication. OpenGL coordinates are vastly different than mug coordinates. While mug's coordinates range from 0, 0 at the top left to the dimensions of the graphic at the bottom right, allowing for a pixel by pixel coordinate space, so to speak, OpenGL does things vastly differently and uses normalized device coordinates, or NDC for short. In OpenGL, 0, 0 is the middle of the screen, with all x and y values lying between -1 and +1, which is vastly different than mug. Increasing the x moves something right, and decreasing the x moves something left, which is the same as mug. But increasing the y moves something up, and decreasing the y moves something down, which is very different from mug. This whole coordinate mess introduces like a million complications in the shader. First things first, I need to translate the given mug coordinates to OpenGL coordinates within the vertex shader. Part of calculating that requires me to know the dimensions of the rendering space, which GLSL does not automatically give you access to in the vertex shader as far as I'm aware. The way I decided to retrieve this data was via a uniform, which allows you to declare a variable in the shader and set the value for it from the CPU. Trust me that this variable stores the dimensions of the rendering space. Actually, it stores the dimensions divided by 2 because that's easier to use in the calculations. Speaking of which, after enough fiddling around, I came up with these 2 ways of calculating the OpenGL coordinates, one for the x coordinate and one for the y coordinate. I found it out pretty much by brute force. I won't explain it too thoroughly, but you basically just take the mug coordinates, subtract the half dimensions, divide it by the half dimensions, and then make the y-coordinate negative to adjust for the flipping of the y-coordinate between mug and OpenGL. The z-coordinate requires no modification within the shader. I'll get into making the z-coordinate work properly in a bit. So, with the coordinates calculated in the vertex shader, I have now specified how to take the raw point data that I defined earlier and convert it into OpenGL coordinates, which OpenGL can then use to render as individual vertexes. There is one more thing that I need to handle within this shader though, and that is the color data. The fragment shader handles filling in the color of each pixel, but only the vertex shader has direct access to the buffer data. This means that I need to transfer the color data of the object from the vertex shader to the fragment shader, otherwise the fragment shader will have no way of knowing what color to fill the object with. Thankfully, this is pretty easy. In the vertex shader, I just declare an out variable, which sets it up to be sent to the fragment shader down the road. I then just set the value of this equal to the color of the point. With that handled, I can then get to work on the fragment shader, which is thankfully much simpler. The fragment shader handles the coloring in of pixels. Once the vertex shader has been used by the GPU to figure out how the shape is formed via determining the position of each vertex, which I did tell it how to do, it then uses the fragment shader to process pixels within the shape's boundaries, giving me direct access over how the color of each pixel within the shape is calculated. How exactly the GPU decides which pixels to fill in and not based on the vertexes depends on a few things, primarily the primitive type, but I'll get to that later. What I want to focus on for now is the ability to calculate each pixel's color, which is about as powerful as it sounds. Most of the fancy shaders I showed you before are basically just beefed up fragment shaders, and I'm definitely going to be taking minor advantage of this power down the road. But in the context of trying to render a single point, my job here is really simple. Set the color of the pixel to the color of the point. There's two primary variables that need to be defined in the fragment shader. The first one is the color of the object, which is being sent to me from the vertex shader, who has access to the object data. The color is retrieved by defining an in variable that corresponds to the vertex shader's out variable and allows me to directly receive the value from the vertex shader. The second variable I need to declare is the out variable, which is used to tell GLSL what color I ultimately set the pixel to. This acts as the output of the fragment shader. And ultimately, all I end up doing in the shader is setting the pixel color to the color of the shape. Nice and simple. With these shaders written and stored as strings to send to OpenGL, which makes them look kind of ugly, I now need to compile them and create a shader program out of them, which allows them to be used to render objects. This just involves writing a lot of OpenGL boilerplate, telling OpenGL where everything is and setting up everything, but it eventually results in this shader program handle. This shader program wraps up the functionality of both my vertex and fragment shader into one object, which I can then use to render buffers with down the road. I simplified this whole process into a single function that just takes in code for a given vertex and fragment shader and returns a newly created shader program. Whenever I want to use the program, I call GL_useProgram. From there, any render calls made in OpenGL will be performed with the program until another program is binded. And whenever the program needs to be destroyed, I simply call GL_delete_program on it. The point shader program and any future shaders that I make are all going to be stored in this one struct, muGL_shaders. This struct is then stored in the OpenGL context, allowing the shaders to be permanently stored as long as the graphic exists. So now I can theoretically use shaders, but now I need actual data to render, and this is where buffers come in. I won't bore you with the details of how to do exactly what I describe in the OpenGL code, since this is one of the parts of the OpenGL API that I'm not a particular fan of, but I will describe what it's doing conceptually. Basically, I have the original mug points array on the CPU, and I need to create a buffer on the GPU that represents the same data. Like I said before, these two representations can be different from each other, and this will be taken advantage of later, but for now it'll largely be one-to-one. Now, the challenge here is this. Each buffer behaves differently depending on what object it's representing. How the buffer is going to be described, filled, and rendered all differ depending on if it's storing data for a point or a triangle or whatever. So to resolve this, I decided that for each object type, I'd make a basic set of functions that take in a given given buffer and perform those basic operations of describing, filling, and rendering. Most of these operations are heavily reliant on how the shader for the object type is defined. For example, I want the way the buffer is described in this function to match how it's described in the vertex shader, since the vertex shader is set up to read practically directly from the buffer. So in the function that describes a buffer for the point object type, I just describe it in the exact same way that I describe data for the point vertex shader. That covers describing a point buffer, aka setting up how the buffer will be stored on the GPU. Now I need to be able to fill a point buffer, aka actually move the data from the CPU to the GPU. For that, I created a function that just loops through a list of points and copies data from it into the buffer according to the buffer's description. This is essentially the code that translates the actual mug point list on the CPU to the buffer on the GPU. Now that I can describe the buffer, telling the GPU how it's formatted, and fill the buffer, giving it the actual data, the last thing I need to describe is how exactly the buffer is rendered. For this, the function GLDrawArrays exists, which can be used to render a given buffer using several primitive types.
But what's a primitive type, Mr. Move?
Well, I'm glad you asked, and don't call me that, please. When OpenGL has finished using my vertex shader to convert the buffer data to a collection of vertexes, OpenGL then needs to decide how these vertexes are connected and then which pixels to fill in using the fragment shader. The primitive type controls this process. For example, the primitive type GLTriangle takes every group of 3 vertexes and uses them to form a triangle, filling in all of the pixels within them using the fragment shader. Something like this will be helpful when rendering triangles, but for now I just want to take my vertexes and render a single pixel exactly where each one is. Thankfully, OpenGL has a primitive type just for this, GLPoints, which does what I want it to here. So I just called GLDrawArrays, specifying GLPoints for the primitive type. There's also 2 other parameters this function takes, and they all specify what portions of the buffer to render, giving an offset into the buffer to start from, in vertexes, and how many vertexes to render from the buffer. So I created 2 rendering functions for points, a function that renders the entire buffer, giving no offset and rendering for the length of how many vertexes there are in the buffer, and a function that renders a portion of the buffer, taking in and using a given offset and length. These align with the rendering and sub-rendering functions I specified in mug a while back. With these 2 rendering functions, I now have my complete set. I have a way to describe, fill, and render a point buffer. From here, I just had to write a bunch of code wrapping everything up and organizing it all within the OpenGL code. This includes stuff like writing some boilerplate around buffers, handling the actual explicit creation and destruction of the buffer, as well as some boilerplate for handling how the point functions eventually get called on a buffer. This is also where I handled actually updating the values for the dimensions uniform in the vertex shader, which you might remember if you're mentally insane. During this time, I also handled specifying how the z-coordinates should be interpreted by OpenGL, specifying that vertexes with greater z-coordinates render over vertexes with smaller z-coordinates. And after all of this OpenGL code cleanup, I wrote the high-level mug functions I defined earlier to call those OpenGL functions, and with that, I can now theoretically render objects. To test it all out, I wrote a quick point rendering demo that renders a single pixel onto the screen, and after writing and compiling it, if you look really closely, you'll see a single pixel. Epic. And to test that I could also keep refilling the buffer with different data each frame, I expanded the demo a little bit to render a trail of points moving using this weird function I came up with after slamming my head on my keyboard in Desmos for a bit. Each point also has a completely randomized color, which I think looks kind of cool. With all of this set up, it's actually pretty easy to get another object type working, lines. For defining the line, the struct mugLine is simply just 2 points. This does mean that the 2 points of a line can be different colors, to which OpenGL will automatically blend between the 2, creating a smooth gradient. And for actually handling the OpenGL code for rendering a line, most of it is entirely the same as the point code, since the only real difference between rendering a point and rendering a line is the primitive type. While I can use GLPoints to take a list of vertexes and draw a point for each one, I can use GL lines to take each group of 2 vertexes and connect them together using a line. Because of that, I can just mostly recycle the shader and buffer functions from the points and simply define the rendering functions as using GL lines instead of GL points. I also recycled a lot of the code from the point rendering demo I just made to create a line rendering demo. I just made the trail a collection of connected lines and made the trail go on for much longer. And just like that, I now also have lines rendering. They may look extremely smooth, but that's just because there's a ton of lines to define all of the curves. Okay, pixels and lines are all fun, but I want to get some actual good full shapes rendering. Like, let's get the classic OpenGL triangle rendering. Well, what if I told you that rendering a triangle is virtually as easy as rendering lines? A triangle, mug triangle, can be defined as just 3 points, much like how a line is just defined as 2 points. And in OpenGL, much like rendering lines, the only major difference between rendering triangles and points is the primitive type. Instead of using GL lines, I use GL triangles, which takes every group of 3 vertexes and forms a triangle out of them, filling in all of the pixels within the triangle's boundaries. So yes, rendering a triangle is just that easy. And after setting up a demo with some quick and dirty math, I created this, a triangle whose point colors fade over time. And so easy too, since I really did all of the hard work when I was creating the points. The next thing I wanted to try rendering was a rectangle, and this is where there starts to be complications worth talking about. We can already theoretically render a rectangle, since a rectangle can really just be represented by 2 triangles, but it's actually for this exact reason that OpenGL has no built-in support for rendering rectangles as a primitive type. So shouldn't Mug follow suit and make the user define 2 triangles if they ever want to render a rectangle? This is debatable in my opinion, but personally I wanted to be able to provide the convenience of being able to just define a rectangle instead of having to define 2 triangles each time. Also, being able to render rectangles will make it easier to render other more complicated objects that I'll get to in a moment, so either way I think it's better to provide them than to not. To start, I defined the rectangle object as the struct muRect, which is defined by a few things: the center point of the triangle, its width and height, and rotation around the center point. Using these attributes, you can define virtually any rectangle you'd like. There are a few limitations of defining it like this though. For example, since the rectangle isn't defined as 4 points connected together, instead only being defined by the center point, you can't make the rectangle have different colors for each corner. The rectangle has to be one solid color. Ultimately though, I wasn't particularly concerned by this, primarily because there's always the fallback of defining it with 2 triangles, to which you can then set the colors of each triangle's individual corners. And either way, I think the inconvenience of having to specify the same color for all 4 corners each time you want to draw a solid color rectangle would largely outweigh the benefits. I could have made it a separate object, but I honestly just couldn't be bothered to, although I might implement it in a future version if it becomes an annoying issue. Now, actually implementing rectangles in OpenGL is a little bit tricky. Like I said, there isn't any rectangle primitive type, so I'm gonna have to find a fairly efficient way to render rectangles using triangles. The most immediately obvious way is to use the same primitive type, GL triangles, and simply form 2 triangles for each rectangle. But this ultimately leads to me repeating a lot of vertexes. Take this rectangle, for example. If I split it up into 2 triangles, I have to define the first triangle by defining these 3 vertexes. But then, to define the second triangle, I define these 3 vertexes. You can see that 2 of the vertexes are literally exactly the same, existing in the same position with the same color, and this repetition in data would exist for every rectangle, which is quite inefficient. There is a simple and widely known way to fix this issue though, and that is index buffers. So far, I've just been using a single GPU buffer to define all of the data that goes directly to the vertex shader. Despite me not using the phrase directly, this buffer has been the vertex buffer, since this buffer holds every vertex as they're individually defined. However, an index buffer can be used to modify the way that OpenGL interprets and sends this data to the vertex buffer. An index buffer, as the name implies, stores a list of indexes. Each index references a particular vertex in the vertex buffer, and can be used to change the order in which OpenGL sends these vertexes to the vertex shader. For example, let's take the rectangle from before and in the vertex data only define it as the 4 unique points. In order to send these vertexes in groups of 3 for OpenGL to then turn into triangles, I'll use the index buffer to modify the order of the vertexes. First, I'll take these 3 corners and order them in the index buffer to form this triangle. Then, I'll take the 3 opposing corners and form another triangle out of them, again just referencing them by index in the index buffer. With this setup, OpenGL will form 2 triangles, using the 4 vertexes I've defined in the vertex buffer and the 6 indexes I've defined in the index buffer. This ultimately saves space, since compared to the previous method, I've had to define 2 less vertexes and define 6 indexes. A single vertex is actually quite expensive, given that it holds floating point information like the position and color of the vertex, while an index is a single integer number, meaning that this trade is overall worth it in terms of how much data a single rectangle takes up overall. Using index buffers does introduce more complications, since now for some object types I have to store and manage 2 separate buffers. I won't go too in detail about how this was performed because, again, OpenGL buffer code, but this does involve creating a function for filling in the index buffer, which just generates index values in the pattern to form triangles. It also involves using the function glDrawElements instead of glDrawArrays, which can be used to render using a vertex buffer and index buffer together. Calculating the offsets for subrendering was a bit wonky using this function since it wants the offset into the index buffer in bytes, but it ultimately works. The most complicated part of making this all work though is actually converting the array of mugrecs on the CPU into vertex data that can be read by the shader, which, if you'll remember before, I called filling the buffer. So far it's been fairly straightforward since the definition of the objects I've made so far have usually been quite similar to how they're defined in the vertex data. However, this is the first object whose definition is quite different from how it would be represented in vertex form, since I decided not to define mugrect as 4 points, but instead 1 center point with a width and height and rotation. This means that when I'm converting a mugrect into actual vertex data, I need to expand it into 4 vertexes, which includes calculating the position of all 4 vertexes rotated around the center. This wasn't particularly easy to do in C, but wasn't insanely difficult either. It's just a bit hard doing math like this in C. And to test the functionality of rectangle rendering, I made this demo with 2 little rectangles spinning around each other. It's beautiful. This chapter, I ascend. I've been forsaking the raw power of the fragment shader, a power which I mentioned briefly before. Up to this point, actually, I've still been recycling the exact same fragment shader used for rendering points, since I haven't been doing anything particularly fancy regarding calculating the color of each pixel. Just set the color of the pixel to the color of the vertex. I'd like to elaborate more on this power that I wield and use it to render more advanced shapes that aren't traditionally that easy to render on computers. So a fragment shader gives me the ability to calculate the color of each individual pixel, we know that. However, have you really thought of what that means? For example, let's just take a generic square that's being rendered by the rectangle shader, which I've defined before. Each pixel has 4 channels, red, green, blue, and alpha, with the most interesting one to me being alpha, which controls how transparent the pixel is. Theoretically, using the fragment shader, I can turn any set of pixels on or off by setting the alpha to 1 or 0, which can cut the square up into virtually any shape I want, like a circle, for example. I would just need to come up with some code or algorithm that figures out whether a given pixel should be visible or invisible based on its position. So I set my goal on this. I want to render a circle using this mug circle struct made up of a center position and a radius, which would expand to a 4-vertex square similarly to how the rectangle expands. Cutting this square into a circle could theoretically be achieved by calculating whether or not a given pixel is inside or outside of the circle. If it's inside, return the normal vertex color. However, if it's calculated to be outside, set the alpha to 0. This sets all pixels outside of the calculated circle boundary invisible, giving the appearance of a circle by just sort of cutting out its shape out of the square. But like anything that sounds cool, it's considerably easier said than done, and there's a few complications I have to come over before I can start cutting up this square. In particular, I need to know a few things in the fragment shader before I can start calculating whether or not a given pixel is inside or outside of the circle's boundaries. The laundry list of variables needed in the fragment shader to calculate this is the following: the position of the current pixel, the center position of the circle, and the radius of the circle. The first needed variable, the position of the current pixel, is thankfully really easy to retrieve, as GLSL provides the variable glFragChord in the fragment shader, which represents the position of the current pixel on screen, which is super helpful. The next needed variable is the center position of the circle, and this is where things kind of get hard. You see, the fragment shader, as I've programmed it so far, has no idea where any of the vertexes are. This is intentional, as I haven't really needed to know that, since all the fragment shader has done is return the color of the vertex being rendered. So I should just pass the circle's center position from the vertex shader to the fragment shader, which should fix the issue, right? Nope! Try again. The vertex shader doesn't know where the center of the circle is either. Remember, all I'm doing here is taking a square and doing fancy fragment shader math to cut out a different shape. And since all the vertex shader does is take a given vertex from the vertex buffer and calculate its position, all the vertex shader knows at once is whatever corner of the square it may be on. So the conundrum here is this. In the vertex shader, given just an individual vertex from the buffer, I need to know the center of the square, which I can then pass to the fragment shader to let it do fancy math. The best solution I could come up with for this is simply defining the center position of the square for each vertex, which allows the vertex shader to know the center even though it's only aware of an individual vertex. This is unfortunate since it leads to a lot of repetition in the data, since I have to redefine the center of the square for the vertex data in all of its 4 corners, but I'm not aware of a better way to fix this. But thankfully, with this change to the vertex data, I am able to retrieve the center of the square in the vertex shader, which means that I can just pass it to the fragment shader. So in the fragment shader, I now know the position of the current pixel and the center of the circle. The last thing I need to know is the radius of the circle. And unfortunately, just like knowing the center of the circle, this would need to be passed from the vertex shader to the fragment shader, and the only realistic way I know of to let the vertex shader know this information is to simply put it in the data for each vertex. So that is an additional value to append to each vertex, which is then fed to the vertex shader, which then gets passed to the fragment shader. But with all of this out of the way, I now know everything I should need to know to calculate whether or not a given pixel is in or out of the circle. And believe it or not, this is actually pretty easy to do mathematically. Now, I am not a math nerd, or at least not that much of a math nerd compared to the average computer science nerd, but I do know that a circle is defined by the equation x squared plus y squared equals r squared, where r is the radius of the circle. Wow! This equation is really just defining all the points whose distance from the center is the radius. All points are equally distanced from the center, with the distance getting bigger and smaller proportional to the radius. So how do I take this equation and turn it into an algorithm that tests if a given point is inside or outside of the circle? Well, I can turn the equals sign into a less than or equal to sign, and magically the circle fills up. This is because before, I was only allowing points whose distance from the center was exactly equal to the radius. However, by changing the sign, I'm now allowing all points whose distance from the center is less than or equal to the radius, only barring out points whose distance from the center is greater than the radius. Setting up the equation like this then naturally fills in the circle, as points within the circle have a distance to the center that's smaller than or equal to the radius. In other words, when given a point with x and y and a circle with radius r, I can just use this formula to determine whether or not it's inside the circle, which is exactly what I want. I can just take the pixel's position and the circle's radius and plug them into this formula, which can then just be used to determine whether or not the given pixel is within the circle or not. Actually, I am slightly simplifying since I also need to account for the center position of the circle. This can be mathematically resolved quite easily though. All I need to do is take the circle formula and offset the x and y by the center position, which performs the math on the position relative to the center position, allowing the circle to move and the check to still be performed correctly. All I then need to do in the fragment shader is implement this formula using GLSL syntax, plugging in the pixel's position, the circle's center position, and the circle's radius in. If this check is false, that mathematically indicates that the pixel's position is outside of the circle's boundaries, and in such a case I simply set the pixel's alpha to 0, making the pixel invisible. If the check is true, then the point is within the circle, and I set the pixel's alpha to 1, making the pixel visible. To test if this works, I just implemented all of the other buffer-related functions needed for the circle. Filling a circle object buffer was actually easier to work out than the rectangles is, since a lot of the complications when expanding a mugrect into 4 vertexes came from calculating the rotated positions. In the case of circles though, I didn't include a rotation value since visually speaking, rotating a circle does nothing, so all 4 corners of the circle's square are pretty easy to calculate by just using the radius to offset from the center of the circle. And since a circle is largely just a cutout rectangle in many ways, virtually all of the other functions were the same as the rectangles. So to test it, I set up a quick demo that features 4 circles rotating around the center of the window, sizing up and down gradually in radius. However, it was at this point that I noticed something interesting. My circles looked bad. You may not be able to tell on this video due to compression, but if I simply freeze a frame of these circles by taking a screenshot and then zoom in, you'll notice that the edges look really jagged. However, if I open Paint.net, the best image editor in the world not sponsored, and draw a circle, Paint.net's circle looks all smooth. This makes sense if you think about it, since I'm simply throwing away any pixel that's outside of the circle's boundaries, meaning that there's no smoothing being performed between the inside and outside of the circle. Actually, this has secretly been happening to all of the shapes I've been drawing so far, because OpenGL also doesn't automatically perform any smoothing. For example, take one of the rectangles I was drawing before in the previous demo. Take a screenshot of it and zoom in, and you'll see jagged edges all over the place. But in the case of these rectangles, OpenGL bears responsibility. This is because when OpenGL has calculated each vertex using the vertex shader, and it's going to use the fragment shader to fill in the pixels for the shapes that these vertexes form, it needs to determine which pixels to actually fill in. OpenGL handles this similarly to how I've been rendering my circle. It simply calculates which pixels are strictly within the boundaries of the shape, and then calculates the color for each pixel using the fragment shader, which ultimately results in a jagged edge since pixels are being strictly determined as being in or out of the shape. The most standard way of fixing this is by multi-sampling, and it's provided by OpenGL. Multi-sampling takes each individual pixel and splits it up into multiple samples. It then calculates the pixel color of each of these samples and sets the overall pixel color to the average of these samples. The edges of the shapes end up looking a lot smoother as pixels near the edge end up gradually fading inside and outside of the shape. However, this smoothness comes at the cost of having to calculate many more pixels, since each pixel involves calculating the value of 4 subpixels. This ultimately means that there are 4 times the amount of pixel calculations being performed. Now, a question naturally arises. If you don't like how jagged the edges of your rectangles and circles are, just turn on multi-sampling. Now, that's a good observation. You get a brownie cookie for asking that. And you'll see that if I change the pixel format of the window to request 4 samples and called GL enable for multi-sampling, the jagged edges on the rectangles are indeed smoothed out. However, you'll notice that the edges of the circles are still super jagged despite the fact that OpenGL is calculating multiple samples for each pixel and averaging them out. Now, why is this? Well, there was something that I was unaware of. Multi-sampling does not calculate multiple samples for each pixel. It only calculates multiple samples on the edges of primitive shapes, as it would be inefficient to perform multi-sampling on a pixel that's 100% within the shape. And since I'm hackily drawing a circle by kind of cutting out its shape by setting certain pixels as alpha values to 0, OpenGL doesn't know to perform multi-sampling on the circle's edges. The term for actually performing multiple samples for every pixel is, funnily enough, called super sampling, but I don't think I'll implement it since I think there's a fair chance that it can drastically decrease performance. So if multi-sampling isn't going to fix my issue, and super sampling will, but at a cost I don't think is worth it, what am I to do? Well, if super sampling can fix it, then super shader math might. The idea is this: instead of just using an algorithm to check if a pixel is inside or outside of the circle and correspondingly just setting the alpha to 1 or 0, what if I instead came up with a formula that naturally blends the alpha values for pixels near the edge of the circle? Like, the formula would return 1 for pixels that are fully inside the shape and would return 0 for being fully outside of the shape, but then return smooth values between 0 and 1 for pixels that are dancing right on the edge of the shape. This mystery formula could be used to just calculate the alpha value of each pixel and would theoretically automatically smooth out the edges of the circle with no multi-sampling required. However, the eternal rule remains true. Easier said than done, because mathematically speaking, this formula is a little more complicated to figure out than the one I've been using so far. A good place to start would be setting the stage. We have a circle whose center position is C, a radius for the circle, and a pixel whose position is P. The first thing I want to figure out is how far away the pixel is from the closest edge on the circle. Well, I don't know how to calculate that, but I do know how to calculate the distance between the pixel and the circle's center position. This is because I know both of these points, meaning that I can just plug the points into the fancy distance formula, and just like that, I have the pixel's distance from the center of the circle. As the point gets closer to the center, the value gets smaller, and as it gets farther away, it gets bigger. So how do I turn this into the pixel's distance from the closest edge of the circle? Well, think about this. The distance I get from this formula is always going to be greater than or equal to 0, since it wouldn't make sense for a distance to be in the negative. So if I subtract the radius from this distance, this has an interesting effect. When the pixel is directly at the center, it equals negative radius of the circle, since the distance at that point is 0. And when the pixel is directly on the edge of the circle, this distance equals 0, since the distance at that point also equals the radius. This means that, according to this formula, when the value is negative, the pixel is in the circle, and when the value is positive, the pixel is outside the circle. However, more importantly, the transition between these two now gradually changes depending on how close the pixel is to the edge of the circle, since I'm performing these calculations with the exact distance from the center of the circle. From here, it's all about making this formula equal a number that I can just plug in as the alpha value for the pixel. To achieve this, I first made what I've written so far negative, so that the inside is positive and that the outside is negative, and then I added 0.5 to the whole thing. This makes it so that when the pixel is right on the edge of the circle, the value is 0.5. As you move in, it goes up to 1 and beyond, and as you move out, it goes down to 0 and below. From here, all I have to do is clamp the value so that it's not any greater than 1 or less than 0, and just like that, the formula is complete. If the pixel is fully in the circle, the value is 1. If it's fully outside of the circle, its value is 0. And when the circle is close to the edge, it gradually transitions between the two values. If you then plug this formula into the alpha channel of every pixel, you should theoretically get automatic edge smoothing. So to test it, I replaced the previous formula in my GLSL code with this more fancy formula. Now, if I take a screenshot of the circle demo and zoom in, you'll see some nice smoothness with no multi-sampling or super sampling required. It's just beautiful. Now that I had proven my theory of cutting out any shape I want with fancy shaders, I also wanted to implement just a few more fancy shapes, the first of which that I was interested in being the squircle. And for the first time in my life, I was able to learn and understand a mathematical concept from Wikipedia, which has this beautiful equation for a squircle. To quickly explain it, I'll start with the classic circle equation again. If you look at the equation closely, you'll notice that there's only one number that hasn't been explored that much in the equation so far in this video. The exponents, those 2's that every number is set to the power of. If I swap out these 2's with another variable and change that variable to another number, say 4, it starts to become a lot more square, same for 6 and 8 and on. But if I set it to an odd number, the square breaks up in all quadrants except for the quadrant where both x and y are positive. Taking the absolute values of the x and y coordinates forces them to be positive all the time, fixing the issue and giving a clean and nice squircle across all 4 quadrants. The higher I set the exponent, the more square it gets, and the lower I set the exponent, the more circular it gets. Now, like before, I could just turn this into a greater than or equal to check to cut out the shape in GLSL, but I also want squircles to have smooth edges, so I have to come up with another formula that gradually transitions between 1 and 0 near the edges of the squircle. But because the equation for the squircle is so similar to the circle, I'd like to come up with this new formula by starting with the smoothing formula for the circle and then modifying it to work with a squircle. The first thing that I'm going to do is I'm going to take these 2's and turn them into the exponent variable, and then wrap the x and y in an absolute value, since that's actually all I did to the original circle equation to make it a squircle if you think about it. And this is actually almost it. However, I missed one secret too, and that's the square root. The square root simply finds the second root of a given number, so if I replace this 2 with the exponent variable, it will then find the nth root of the number. And just like that, the new formula has been created. It equals 1 when the pixel is fully inside the squircle, 0 when the pixel is fully outside, and fades between the 2 values near the edge. And this value is always accurate no matter what value I set the exponent to. Before I start working on making the shader for this though, I actually need to define a struct for the squircle, which I hadn't done yet. I decided to make the struct for a squircle, mugsquircle, the same as mugscircle, except for 2 additional members. The first gives direct control over the exponent variable that controls the roundness of the squircle. The second is a rotation value, which didn't exist before for the circle since rotating a circle visually does nothing, but now since the roundness of a squircle's edges can be changed, rotation can indeed visually change a squircle. Now, before I get to the fragment shader for the squircle, it does need to know quite a bit of information beforehand, similarly to the circle's fragment shader. I still need the center position of the squircle and its radius, but I also need to know the exponent variable and the rotation, since both of those influence how I'm going to implement the formula. So both of those also need to get shoved into the vertex data, making each vertex actually surprisingly expensive, but hey, what are you going to do?
What are you gonna—
Anywho, with that data then passed from the vertex shader to the fragment shader, I can now write the formula into GLSL, which looks like this. Truly readable if you ask me. But there is one more important hurdle I need to overcome with the way I've set this all up. I need to account for the rotation. The square that I'm cutting the squircle out of now may be rotated, so I need to adjust for the rotation within the formula. Thankfully, this is really simple. If I just rotate the pixel's position beforehand and then plug it into the formula, it mathematically all checks out. To test all of this, I quickly whipped up this demo with some spinning squircles that gradually change in roundedness. And yes, if you take a screenshot and zoom in, you can see some nice, smoothed out edges, meaning that the fancy algorithm does work. Now, there was one more cool shape that I wanted to implement before I was satisfied, and that is the rounded rectangle. You may be a bit confused by that, since a squircle kind of is just a rounded rectangle, and the terminology is kind of mixed up from what I've seen. I use the term squircle to refer to what I've already got rendering here. I use the term rounded rectangle to refer to a rectangle but with circles drawn at its corners, which when filled in visually appears to be a rounded rectangle. My primary reasoning for wanting to get this working at the time was that since a rounded rectangle is a rectangle, it's easy to just make it wider or taller with it still visually looking good. The only way you could do that with a squircle would be by stretching it out, which I presumed would look bad. But then I realized that a stretched out squircle honestly doesn't look that bad and actually looks better in my opinion. For example, I'm pretty sure the YouTube logo uses a stretched out red squircle for its background shape. I'll probably go back at some point to implement a width and height for squircles instead of just giving a radius, since mathematically it's super easy to work out, but I'll save that for another time. Anywho, believe it or not, the rounded rectangle was the hardest for me to implement. Obviously, I'm going to need to make a smoothing formula for it, but I struggled to even find a formula definition for a rounded rectangle at all. From what I can tell, it's impractical or outright impossible to define a rounded rectangle in just a single nice and neat formula, since it would have to incorporate both the rectangle and all of the 4 circle corners. So I had to come up with a series of variables and checks that gradually form the rounded rectangle. I'll define the rounded rectangle's width and height, as well as the radius of the circle that acts as the rectangle's rounded edges. I'll then also define the point P, and the challenge here is to determine if the point is inside or outside of the rounded rectangle. To work this all out, I'll smack the center of the rounded rectangle at 0, 0. The first part that I want to work on is the rectangle without the circle corners, which looks like this. This can then be split up into 2 rectangles. Whether or not the point is in one of these rectangles is fairly easy to figure out. For example, a point is in this wide rectangle if it passes these 2 checks. First, the absolute value of the x-coordinate must be less than or equal to the width divided by 2, and second, the absolute value of the y-coordinate must be less than or equal to the height divided by 2 minus the corner circle radius. All of this might be confusing at first, and the divisions by 2 and absolute values probably aren't helping, so it's best to think of these checks relative to whatever quadrant the point is in. For example, let's look at these checks closely if the point is in this quadrant, where both x and y are positive. The first thing that you might notice is that since the rounded rectangle is split up into 4 even sections by the axis, we're only primarily concerned with the width and height when they're divided by 2, which explains the divisions by 2 for the width and the height in these checks. The subtraction of the radius also begins to make sense, since subtracting the radius from the height essentially cuts off the top corner of the wide rectangle. To understand the absolute values, I'll take them away, which leaves this quadrant that we've been looking at so far completely unaltered. However, if we then zoom out to the other 3 quadrants, you'll notice that the rectangle just never ends. This is because we're performing a less than or equal to check on the x and y values compared to a positive number, and in these other 3 quadrants, at least the x or y are always negative. In fact, in this quadrant, both the x and y are always negative, meaning that the check is completely useless in this quadrant and all points pass the less than or equal to check. This is fixed by just taking the absolute value of the x and y, which flips any possible negative number to being positive, making the check virtually identical in all 4 quadrants. This whole process can then be repeated for the tall rectangle. The absolute value of the y value must be less than or equal to the height divided by 2, and second, the absolute value of the x value must be less than or equal to the width divided by 2 minus the corner circle radius. You can see how this is kind of just what I wrote before, but with the variables swapped around. With these 2 checks, I can then define whether or not the given point is within the rectangle part of the rounded rectangle. However, if the point is not in these 2 rectangles, then I need to perform checks to see if it might be in one of the rounded corners. It seems like it would be impossible to perform just one check that could see if the point is in one of the rounded corners or not, since there's 4 individual corners, but it is possible. First, I'll try and check if the point is in this circle edge, the one that's in the quadrant where both x and y are positive. I already know the formula for checking if a point is in a circle. X squared plus y squared is less than or equal to the radius squared. But that puts the circle in the middle. I need it in this corner up here. If I offset it by the width divided by 2, it gets the circle closer, but it's too far to the right. Offsetting it to the left by the radius gets the circle closer. It now needs to be raised, and similarly to the x value, offsetting it by the height divided by 2 gets it closer, but then it goes too far up and it needs to be offset by the radius to finally end up in the right position. So this circle does represent the top right corner, but it doesn't check for the corners in the other 3 quadrants. So how can I fix this? Well, in the checks for the rectangle, I was able to get all 4 quadrants to act the same by taking the absolute value of x and y. So I can do the same thing here. I take the absolute value of the x and y, and just like that, the check is performed on all 4 quadrants, forming all of the 4 corner circles with just one check. Combine the checks for the wide and tall rectangles with the check for the corner circles, and you can use all of these to check if a given point is within a rounded rectangle or not. Now, like with the previous shapes, this isn't enough. I need a smoothing formula that gives me a smooth alpha value transition along the edges. Thankfully, this doesn't actually need to be performed for the rectangles, since the only part that would need to be smoothed out would be the edges, and since those edges are on the actual edge of the rectangle that we're cutting out of, OpenGL can already perform multi-sampling on them to smooth out those edges. However, the same cannot be said about the corner circles, so I need to turn its check into a smoothing formula. Thankfully, this process is quite easy. This algorithm is already disgustingly close to the normal circle equation, since all I really did was add and subtract some values to the x and y within the parentheses when they're being squared. So I can simply take the normal circle smoothing equation that I already made, and I can go ahead and add and subtract those values to the x and y within those parentheses, as well as taking the absolute value of the x and y. And this equation does indeed work, smoothing out the alpha values nicely for all 4 corners of the rounded rectangle. So, that's all of the complicated math stuff I need, and implementing this in GLSL was really simple. First of all, I needed to define the vertex data for a rounded rectangle, which is actually quite a lot given how much is needed to calculate the rounded rectangles as boundaries. Obviously, I need the position and color of the vertex, but I also need the rotation of the rounded rectangle, the center of the rectangle, the dimensions of the rectangle, and the radius of the corner circles, since that's all the stuff I need for my formulas. I then pass most of this information to the fragment shader, where I can begin actually implementing all of these fancy formulas. For the given pixel, I first check if it's inside one of the 2 inner rectangles using the checks I created before. If the pixel is in one of them, the alpha can just be set to 1, since I don't need to perform smoothing on the edges of the rectangles. However, if the pixel isn't in one of them, then it might be in one of the round edge corners of the rectangle, and for that, I just set the alpha to the result of the smoothing formula I wrote for them. And just like that, the rounded rectangle is finished. To test it, I wrote up this demo, and by wrote up, I mean I just took the squircle demo and slightly tweaked it to use rounded rectangles, gradually increasing and decreasing the radius of the rounded edges over time. And if I take a screenshot and zoom in, you can indeed see some nice, beautifully smoothed out circle edges. And you can also see the rough edges of the rectangle, since I didn't write a smoothing formula for those. And like I said before, since these rough edges are actually on the edge of the primitive shape being drawn, OpenGL can fix them automatically by just turning on multi-sampling. With some cool 2D shapes rendering, there was one last thing I wanted to get out of the way before I'm largely done with Mug for now. I want to render textures. In case you're unaware, one of the most common ways to internally store and render images on a computer is by representing them as a bitmap, which defines the image as a collection of pixels. The image's width is how many pixels are stored horizontally, and the image's height is how many pixels are stored vertically. The total amount of pixels in an image is the width multiplied by the height. How each pixel is stored can generally depend on 2 things regarding the image. 1, what channels are used, and 2, how big each channel is. For example, a very common way pixels are stored in images is by giving it 3 channels, red, green, and blue, and making each channel 1 byte, giving each individual channel a range from 0 to 255, allowing for 16,777,216 possible colors, which is usually enough. OpenGL, and most other graphics APIs for that matter, allow you to render textures onto the screen primarily by bitmaps. OpenGL's usage of images is fairly simple. You just do some boilerplate to generate a texture handle, set some filtering and wrapping parameters, which I'll explain in a moment, and give OpenGL the bitmap data with some additional information about how it's formatted. From there, since the color of each pixel is ultimately decided in the fragment shader by me, If I ever wanted to render textures onto the screen, OpenGL needs to give me a way to access the color data of the image from the fragment shader and return it as the pixel color. For this reason, OpenGL provides samplers, which can be used to sample from a texture. In the fragment shader, I declare a uniform variable whose type is sampler2D, representing the data of some texture, which I'll get to in a moment. To get a pixel color from the texture, I then use the texture function, providing what sampler I'm getting the data from and the position on the texture that I'm sampling from. This can be used to read color data from any point on a texture and return it as the pixel color in the fragment shader, which can theoretically be used to render textures onto the screen. The exact texture that the sampler is sampling from depends on the currently binded texture, which is decided outside of the shader. You can set this texture by calling glBindTexture on whatever texture you'd like before rendering with whatever shader and buffer you're going to use. There's a few ways to customize how the sampler decides what color to return given a point on the texture. That's what those filtering and wrapping parameters were all about. The filtering parameters specify how subpixel positions are handled. The fragment shader is now requesting pixel positions that lie between multiple pixels in the texture. What the sampler does here is dependent on the filtering for the image. For example, OpenGL provides the filtering type GLLinear, which blends the pixels as values together. Overall, this creates a blurry looking effect on images that have been considerably upscaled. OpenGL also provides the filtering type GLNearest, which simply sets the color to the nearest pixel, which creates a jagged, pixelated look on upscaled images. The wrapping parameters of a texture specify what color should be returned when an out-of-range texture coordinate is requested. OpenGL provides several ways to set the handling of this situation for a given texture. GLRepeat simply repeats the image for all out-of-range coordinates. GLMirroredRepeat does the same as GLRepeat, but mirrors it repeatedly. GLClampToEdge returns the closest in-range pixel, leading to a stretched-out effect. To begin implementing all of this stuff in Mug, I first defined a way that you could create, destroy, and bind a texture, with it working fairly one-to-one with how OpenGL does it, although with less boilerplate, in my opinion. From there, I needed to create an object type for textures, since a custom shader for rendering textures would need to be written. For this, I created the textureRect struct, which represents a rectangle with the currently binded texture being rendered on top of it. The struct has all of the same stuff as the normal rect object, except for with two additional members, the position and dimensions of the texture cutout, which can control what portion of the texture is being rendered on top of the rectangle. And, unlike virtually everything else in this video, this was really intuitive and straightforward to implement in OpenGL. I wrote the standard boilerplate for creating, destroying, and binding the texture. I created the shader who samples from the texture based on the texture cutout, and that's pretty much it. I created this demo to test it, which makes this gradient bitmap using a fairly simple algorithm that increases redness on the x-axis and greenness on the y-axis. It then creates a texture based on that bitmap and then renders it to a spinning texture rect, which you can see here. Now, if you're a particularly astute viewer, and you do get a ton of brownie points if this is true, you may have noticed that there's no reasonable way that you can render a lot of textures at once, since every render call can only have one texture binded. Now, OpenGL does let you render multiple textures at once. You can have multiple textures binded to multiple samplers in just one shader. But there's a big reason as to why I haven't done this. Most of OpenGL's features have defined limits that you can check. For example, you can check the maximum texture size that the current device can support when creating a texture, and there's also a minimum texture size that all devices must support for my version of OpenGL. However, I couldn't find any such limits for how many samplers you can fit in a shader, which makes it practically a guessing game as to whether or not your shaders will work at all. On some devices, I've had it stop working at just 8 samplers in one shader. So I couldn't find a way to practically implement this, although there may just be some limits buried deep in the documentation that I've yet to find. But this situation puts a real thorn in virtually all texture rendering in mug, as for every unique texture being rendered in mug, there needs to be a separate render call to bind the texture and render that particular texture, which is annoying at best and horribly inefficient at worst. Thankfully, there are some ways that you could remedy this issue. In fact, with what I've provided, you can already come up with some clever ways to render multiple textures with just one render call, or at least make it look like you are. For example, let's say I have these 3 images that I want to render using 3 separate texture rectangles, but I want to only have to bind one texture and call one render function to render all of this. Well, I could actually just put all of these 3 images into one big texture and then use the texture cutout parameters in each texture rectangle to cut out each individual image from the big texture when rendering. One texture is technically being used since the 3 images are all stored in just one big texture, and each texture rectangle specifies its own cutout, allowing them to look like 3 separate images even though they're all cropped from the same texture. But this solution isn't always preferable for several reasons. Arguably the biggest one is the fact that the minimum supported size of an image in OpenGL, in width and height, isn't that big in many versions. In fact, in the version that I'm using, the minimum supported size is 1024 by 1024, let alone dozens of fairly medium to high resolution images. So, is there any hope for rendering a bunch of images in just one texture? Well, yes, and it is called the texture array. You know how a texture has 2 dimensions, the X and the Y? Well, what if you just gave it a 3rd dimension, the Z? In each Z-level layer, another texture exists with the same width and height as all the others. This allows you to store much more image data in just one texture, with the only major downside being that all layers must have the same dimensions. The minimum amount of supported layers a texture array in OpenGL can have in the version that I'm using is 256, meaning that I could theoretically create a texture array with a size of 1024 by 1024 by 256, giving me 256 individual 1024 by 1024 texture layers, which is plenty of enough space to store many high-resolution images all in just one texture. So naturally, I want to implement texture arrays in mug, which was also fairly easy to do. I created the texture array rect, which is the same as the normal texture rect, except for with an extra Z coordinate in the texture cutout's position that dictates which layer in the texture array is being cut out and rendered onto the rectangle. Implementing all of this in OpenGL was super easy. The process for creating a texture array in OpenGL is almost exactly the same as creating a normal texture, and the process for sampling from a texture array in GLSL is almost exactly the same as sampling from a normal texture, so the whole process required very little new unique code overall. To test all of this, I made this demo, which is just a slightly tweaked version of the previous texture demo that uses multiple texture layers to fade between 2 gradients, with each point in the fade being stored as a particular layer, and each layer being flicked through and rendered individually over time. Just take a second to admire this. Truly, nothing is taken for granted here. Okay, that's pretty much all I have for this episode. The next episode will deal with getting font loading and text rendering using TrueType, and considering the fact that you got to the end of this video, you're probably a big enough nerd to like that video too, so stay tuned for that. Bye!